Okay, so today we are going to start about the concept of alternating current and circuit analysis. In the CBSE syllabus or ICSE syllabus, the circuit analysis is only restricted to series connection. So the whole lecture will be divided as per the following. We are first going to see only a resistive circuit, then capacitive, then inductive, then R and C, and then R and L, and last one, the most important, the LCR, including the resonance also in LCR circuit. So to start with, we will start with only resistive circuit. Say that you have this as a resistive circuit with a alternating supply fed inside the circuit. We know that, let us say that current in the circuit is I equals to I0 sine omega t, where omega is equal to 2 pi by frequency, or sorry, 2 pi by time period, or 2 pi into frequency. Okay? Now, as this current gets developed in the circuit, let us say that the potential across the resistance will be equal to I times of R. So I can write potential across the resistance as I into R, where I is equal to I0 sine omega t multiplied by R. This gives you I0 R sine omega t. And this I0 R will be equal to the peak voltage appearing across the resistance. Now, the important thing which needs to be known here is the current is a sine function, as well as the resistance or potential across the resistance is also a sine function. So, the whole chapter of alternating current, especially the circuit analysis, is deal with a phasor diagram. You can also deal with complex number also, but since there are many students who have not taken mathematics in class 12, so for them the complex approach will become very much complex for them. So we will rely on the concept called phasor diagram. What does it say? It says that we are going to plot the variation with the help of the phase of the current and the voltage. So let us try to plot the phasor diagram at time t equals to 0. Now if I put t equals to 0, the phase of current is 0, as well as the phase of potential appearing across the resistance also becomes 0. So if I say this as the 0 line and this as the pi by 2 line, let this as 0, so I can say that the current is along 0 phase as I, and potential is also along 0 phase. So we can make a statement here that in resistive circuit, the current and the potential difference is in phase. That means at any instant of time, if I plot a phasor diagram, say that at any instant of time, if current makes a phase of omega t, then potential will also make a phase of omega t. So basically in the resistive circuit, both current and potential are in phase. This is the first part. In the second analysis, we are going to start the capacitive circuit. That means a circuit with only a capacitance with a potential, or you can say alternating potential or alternating current fed into it. So let us start with that one now. So you have now a capacitive circuit like this. Let us say that the current which is fed into it is I naught sine omega t. Now we know that across of capacitance potential is given as Q by C. That Q is the charge across the capacitance and C is the capacitance of the capacitor. Now we also know that I is equal to dq by dt. So dq can be now written as I times of dt. I you can write as I naught sine omega t dt as this is dq. Now upon integrating, which will give you the total charge q. So the integral form looks like this. Now we know that integration of the sine omega t is minus cos omega t by omega. So I can write this one as I naught omega with a minus sign, and then I can write it as cos omega t. Okay. Now if I put this value of charge q in this equation of BC, what's being I there? BC is equal to Q by C. Okay? Now Q is equal to minus I naught omega cos omega t. So I am going to put that in this equation. So minus of I naught omega C cos omega t. Now minus cos omega t can be written as sin omega t minus pi by 2. Okay? I hope this is clear to you. Now, this can be also written as x of c sin omega t minus pi by 2, where xc is equal to 1 by omega c. Now if you can see here, I am talking about the voltage over here. So this has to be the peak voltage. If this has to be the peak voltage, and in this peak voltage this is the current, so this should have a unit of O. So this xc is equal to 1 by omega c, which is known as reactance. Basically has the SI unit of O. Okay? So I can now write I naught into xc as V naught sine omega t minus pi by 2. Now let us try to see how does the phasor diagram looks like. Now, if you see the current I, it has a phase of omega t, sine omega t. And if you see the expression for potential across the capacitance, it has a phase of omega t minus pi by 2. So if I have to plot a phasor diagram at time t equal to 0, with this as 0 phase, this as pi by 2, and this as minus pi by 2, so what I will get? I will find that the phase becomes 0 for current, so current goes in this direction, I. And now if I put t equal to 0, my phase of capacitance becomes minus pi by 2, so BC goes here, in this direction. So what we can see now is that the current and the potential across the capacitors are not in the same phase. Meaning, as logically it means that current and potential will not be zero simultaneously, nor it will reach the maximum simultaneously. So we can make a statement over here that current leads the voltage by pi by 2. Or you can also make the same statement with the word lagging, and the statement will look like as, or voltage lags current by pi by 2. This pi by 2 over here is this one as minus pi by 2 because the angle is clockwise, so it will be taken as negative. So if I sum up the two circuits, in the first circuit we found that only resistance was there, that the current and the voltage are in the same phase, whereas in capacitive circuit the current and the voltage are out of phase by pi by 2. In the most strict language, the current leads the voltage by pi by 2. Now let us try to see what happens in an inductive circuit. So we are going to start with the inductive circuit now. So we are going to replace the capacitance now with inductor. Now we know that across an inductor current is given, the voltage is given as L di by dt. Okay. So if I have the function of current as I0 sin omega t, then how does di by dt will look like? So di by dt of this function will be I0 into omega cos omega t. Right? If I put this value here, then my potential across the inductor will be I0 into omega into cos omega t, and then at the end we multiply this with the L. So multiply with L. So my equation will look like this: I0 omega L cos omega t. Okay. Let me write this omega L as I0 into xL cos omega t. Now again I can give you the same justification, saying that since this is an expression of potential, so this has to be the peak voltage. In this peak voltage, if this is your current, then this has to be this should have the unit of ohm. So this xL, which is again called reactance, has a SI unit of ohm. Okay. Now let us try to convert this cos function into a sine function. So I can write VL as V0 cos omega t, where your V0 is equal to I0 into omega L, or you can write as I0 times of XL. So cos omega t can be written as sine omega t plus pi by 2. Correct? So what we can see now, if you compare the phase of the current and the voltage, I can see that the current is having a phase of omega t, whereas the voltage has a phase of omega t plus pi by 2. So if I again draw the phasor diagram over here, I will find that at time t equal to 0, this is the phase 0, this is phase plus pi by 2, this is the phase of minus pi by 2. So at time t equal to 0, if I put the current at a phase of 0, then my phase of VL will be at a phase of plus pi by 2. So VL goes here. You can clearly see that the VL is ahead of current when not on pi by 2. So now you can make a statement. And the statement says potential or voltage across inductor leads the current by pi by 2, and in other language you can say voltage, sorry, we start with current now. Current lags voltage by pi by 2. Correct? Now, if I sum up the whole three, you should not have any difficulty in the resistance, because both are in the same place. In capacitance, voltage lag current, and in inductor, voltage leads current. So you can remember that in this format also, called series. This is capacitance. This is inductance. Now if I take the first three alphabets, I will see that capacitance, the one letter which comes first is current. So the one which comes first is leading. So in capacitance, the current leads the voltage by pi by 2. If you take the last three nodes and I'm dealing with inductor, so the letter which comes first is voltage. So you can say that for inductor, voltage leads the current. So that's how a short trick is given to you, so that you can make it clear in your mind that who leads in what circuit. Okay. Now let us try to combine the circuits. So we will start with combining RC circuit now. You have an R circuit and then you have a C circuit. Fed your alternating current. And let us say the current is equal to I0 sin omega t. Say that the potential across VR is across resistance and potential VC is across the capacitance. So this as the resistance R and this as the capacitance C. The potential across both of them is VR plus VC. That is not valid here. So you cannot just simply add them up to find the net potential across the two elements of electricity called capacitor and resistor. So please make sure this is clear in your mind. It is not equal. But if it is not equal, then what is it is equal to? So let us try to combine whatever we have learned so far. Let's draw the phasor diagram again at time t equal to 0. This has plus pi by 2, this has 0 and this has minus pi by 2. Your current is in this line at 0 and we have seen that for resistance the VR will be also in the same phase of current. And if it is a capacitance, then in capacitance voltage lags. The VC. So now you have the voltage VR and VC at 0 phase and minus pi by 2 phase. So the net potential across both of them will be given as V, and that with the help of Pythagoras theorem you can say that it will be equal to VR square plus VC square. Right? Let us consider this angle as angle beta. Let us try to understand the mathematics over here. If I have to write the net potential across both of them as V, then we found that the net V can be given as VR square plus VC square. In the form of resistance, I can write this one as I times of Z equals to root over of I times of R the whole square plus I times of X C the whole square. Now the whole I gets cancelled out, so Z will be equal to root over of R square plus X C square. This also you can write as R square plus 1 by omega C the whole square. This Z which is appearing here is called impedance. Net resistance offered by the whole circuit, including the resistance and the capacitance. So this is the net, this is the impedance of a circuit of R and C, and this should also have a unit of ohm. Now, if I can write I equals to I0 sin omega t, then how can I write the V? So V can be written as V0 sin omega t minus beta. Correct? Now, minus beta. I am writing minus beta because the angle is clockwise. So minus beta. This beta can be found out using this logic. Tan beta equals to perpendicular by base. Perpendicular is BC and base is BR. So you can write BC by BR. BC I can write as I when you see this graph here, the cos beta can be written as base by hypotenuse. So base is BR divided by hypotenuse as B, which can be written as I times of R divided by I times of Z. I gets cancelled out. We are left with R and Z. And Z for this circuit we have already found out over there is R square plus XC square. Correct? So what is the summary? The summary is a circuit containing R and C. The net potential lags the current by an amount of beta, which can be found out by using this formula, and the power factor can be found out using this formula. This is the whole analysis of RC, and let me remind you once again that it is not equal to just VR plus BC, rather it is equal to VR square plus BC square. Now let us talk about the RL circuit. So I'm going to run from here. And I'm going to run this part, and I'm going to put the other element, and it's called inductor as L, and let us say this is equal to BL, and this is still valid. If I adopt this, and I have to put this as L, meaning V is not equal to VR plus BL. Then what is this all equal to? So again I will start with the phasor diagram. With this as plus pi by 2, this as minus pi by 2, and this as 0. Now we know that if current is at 0 phase, then VR will be also at 0 phase. Remember we are dealing with at E equal to 0. Then what about VL? Now in L circuit, in inductive circuit, the voltage leads the current. So leading means here. This is your VL circuit leading by pi by 2. So if you have VL and VR, then what is the net resistance across both of them? The net will be given as root over VR square plus VL square. And let me define this angle as again beta. So the net can be now written as VR square plus VL square. V I can write as I times of Z equals to I times of R the whole square plus I times of XL the whole square. All the I gets cancelled out. So Z is equal to R square plus XL whole square. That is equal to R square plus omega L square. And Z here is again referred as impedance, whose SI unit is again ohm. How to find tan beta? So tan beta from the circuit can be given as the perpendicular part and the base part. So VL divided by VR, which can be written as I times of XL divided by I times of R, which is equal to XL by R, which is equal to omega L divided by R. That's how we can beta. Now, if I have to write the potential as V0 sine omega t, then I have to put plus beta here. Reason, because now the voltage is leading the current by an amount of beta. You can see beta is anti-clockwise. So it's a positive angle. So it's plus beta. Where V0 can be written as I0 times of Z, and Z we have already formed over here as root over of R square plus omega L whole square. Okay? And for this circuit, again the power factor is defined as cos beta, and the cos beta is again based by hypotenuse. So base is VR by hypotenuse is V, and that is equal to I times of R divided by I times of Z. I gets cancelled out, you are left with R by Z, which is equal to R divided by root over of R square plus omega L the whole square. Summary. In RL circuit, the potential leads the current by an amount of beta, and beta can be found out using any one of this. And the net impedance is given in this form with the SI unit of ohm, and this is the power factor of inductor R. Potential across R, VR, potential across C, DC, potential across L, VL, and total V is equal to, if I say this is the total V, then it is not equal to VR plus DC plus VL. Very important. Then what is this all equal to? So again we will start with the phasor diagram. With this as plus pi by 2, this as minus pi by 2, and this as 0. The current, if I put t equal to 0, the current has a phase of 0. Okay? What about VR? VR will lie in the direction of I, VR. DC will lag by pi by 2, VL will lead by pi by 2. Right? Then, how will you find the net V? Now, if you can see here, VL and DC are in the same y direction, the y axis. So, this can be subtracted normally. So, I can make another phasor diagram, and I can say that along this y-axis I have VL minus DC. If your VL is more than DC, and this as R, or VC minus VL, and this as VR. If your VC is more than VL. So, if your VL is more than VC, the net potential V will lead the current by an angle beta. If your VC is more than VL, then your net potential will lag the current by an amount of beta. Okay? How do you find the V? We don't have to worry much more about V, whether it is more than VC or less than VC, because the resultant can be given as VR square plus VL minus VC square. So it's a square term, it doesn't matter if it is bigger than no. So that can be also written as Z equals to R square plus omega L minus 1 by omega C the whole square. When it comes to X, I can write as R square plus XL minus XC the whole square. Okay? How will you find the tan beta? So, the tan beta for this circuit can be given as, for particular, it is VL minus VC by R, VR, which can be also written as XL minus XC by R, which can be also written as omega L minus 1 by omega C divided by R. And for this, V will be equal to V naught sin omega t plus beta, where V naught is equal to I naught times of Z. And for this circuit, this condition, tan beta can be written as VC minus VL divided by VR, which is equal to XC minus XL divided by R, which is equal to 1 by omega C minus omega L divided by R. Right? And for this, V will be written as V naught sin omega t minus V. So, the summary says that the net potential is given like this, and if your VL is more than DC, then the net potential will lead by beta, and if your DC is more than VL, then the net potential will lag the current by beta. And you can find tan beta in both the cases also. Now, the important part is this. What if your VL becomes equals to DC? Before that, the cos beta is still the same. Base I have to use VR divided by VL minus VC, which is equal to R, VR divided by V is equal to R by Z, and here cos beta is equal to again VR by V, which is equal to R by Z. has a SI unit. Okay. Now I was saying that what if VL becomes equals to VC? Let us try to see that. So let me rub this part because I need this part. So if I rub this part, if VL becomes equals to VC, that is omega L becomes equals to 1 by omega S. That is omega square equals to 1 by S. That is frequency equals to 1 by 2 pi root over 1 by S. That means when you feed a current in such a way that frequency of the current matches with this value, then we have arrived to a condition called resonance. That means the phasor diagram will only look like this. There is nothing along y-axis because it has cancelled out. Why? Because VN has become equal to VC. That means the cos beta, which is generally written as VR by V, has now become equal to VR divided by root over of VR square plus 0, which is equal to 1. That is, the cos beta has attained a maximum value. That means the power factor in the circuit has become maximum. That is, the current in the circuit is maximum. That is, current is maximum. So this is resonance frequency. In resonance, VL becomes equals to VC. The whole circuit behaves as if there is only one resistance, and L and C effect becomes 0. Current is maximum, and cos beta, the power factor is maximum. Now, how? Let us deal with some graphs over here in this particular case. So, if I have to plot a graph showing the impedance with the current with the frequency omega, I can put F also, then the impedance attains a minimum value at the point when frequency becomes 1 by 2 pi root over of 1 by S. Clearly showing that the impedance has attained the minimum value and has now become equals to R. If I plot simultaneously another graph showing the power as frequency, then I get the graph like this, showing that the power is maximum, the frequency is 1 by 2 pi root over of 1 by S. Correct? So for that particular frequency, the power of the circuit will behave like as if it is responding to that particular frequency a lot. And this is applied in the concept of radios, where you are looking for one particular frequency when you want to tune a particular channel. So basically we tune the capacitance inside the radio as a tuner, and we set the capacitance so that it satisfies to the relevant station, and then you can listen to that particular station only, and rest of our station becomes faded away. So this is the whole scenario of alternating current and its circuit analysis as per the CBSE and IC syllabus. Also, one more small thing, but generally asked for 1 marks and is very important also, is this. Suppose I want to plot XC with respect to frequency. Now we know that XC is equal to 1 by omega C, which is equal to 1 by 2 pi F into C. So basically the graph looks like this. Also, if I have to plot XL with respect to frequency, then we know that XL is equal to omega L is equal to 2 pi F into L. So the graph will look like this. And if I have to plot only R with frequency, then resistance is independent independent of that. So it will just have this current, no dependence at all. So this also they ask for one marks. So with this I conclude my lecture, and I hope you have understood. If you have not understood anything, then just give a comment or mail to me also, and I will definitely try to respond back to you. Thank you.